Okay, so we come to the case of absorbers, such as scrubbers. Scrubbers work like rain system, basically, what I explained about rain. That's how scrubbers work. They have a nozzle fitted in, a spray nozzle of water that may be combined with an absorbent, sorry. Then we have adsorbents such as activated carbon beds and liquid extraction. Okay, so here from the notes, mass transfer is often coupled to additional transport processes. For example, in industrial cooling towers, these towers couple heat transfer to mass transfer by allowing hot water to flow in contact with air, by expelling some of its content in the form of water vapor. Maybe some of us may be familiar to these cooling towers. So the water is cooled by expelling some of its contents in the form of water vapor. So that's a form of mass transfer also. So mass transfer may occur in a gas, a liquid, or solid, and it can also occur across phases. For example, from a gas to a liquid or to a solid. So mass transfer condition there is that there has to be a gradient in the concentration of a species. So there has to be a place of high concentration and a place of low concentration, basically. And the basic mechanisms are the same, whether the phase is a liquid, gas, or solid. So we look at the diffusion phenomena. So diffusion is closely linked, like you said, in some cases it's even interchange with the term mass transfer. So we look at molecular diffusion, we look at counter diffusion also. So molecular diffusion is a process resulting from random motion of molecules by which there is a net flow of matter from a region of high concentration to a region of low concentration. Molecular diffusion or molecular transport can also be defined as the transfer or movement of individual molecules through a fluid by means of a random individual movement of the molecule. So in short, what you have here is molecules who are in a place of a high concentration, okay, and they'll begin this movement to a place of low concentration. So we already have that example. We already had that example that we looked at with Gesho, where we looked at the spray. If someone sprays a perfume, that is basically how molecular diffusion works. Or you'll be passing and you're able to smell some flowers close by as you are walking. You may even be like 2-3 meters away from those flowers, but you're able to catch the scent. That is molecular diffusion. Okay. So the material that undergoes the transport is known as a diffusant or permeant or penetrant. So in this case, okay, you have that movement of the molecular diffusion process. Okay, so molecular diffusion, where the bulk fluid is stationary and the diffusion is primarily by Brownian motion. So bulk fluid is stationary. So in that case, it means that when you spray that perfume, which one is the bulk fluid in this case? So in that case, we have air, isn't it? So in that case, basically, this would be the same as the air around, isn't it? It's stationary. Okay, so what the diffusion is happening by what? Primarily by Brownian motion. Or a case of dye. When you pour liquid dye in a cup or in a bucket, the liquid in that bucket or that cup is stationary, isn't it? So now that is the bulk, because that is more actually than the dye that you're pouring in. So we refer to it as the bulk fluid. So it's stationary. Okay, and then diffusion of the molecules of that liquid dye that you've poured into that, whether blue dye or something, that is now that's where the movement is happening. So this will be moving, isn't it, on its own? You're not even steering, you won't even steer with a spoon, but it's the movement of those molecules is aided primarily by what we are calling Brownian motion. The second case now, in the case of convective mass transfer, the bulk fluid is in motion, okay? And the motion causes mass transfer by both diffusion and convection. The case of, when I say the case of max food that you put in a sink and you open the tap just above it, Okay, so you have the bulk liquid, which is that water coming from the tap, hitting that ice max cool. And then you have that movement happening. And then you have the mass transfer movement happening, which happens both by diffusion and by convection, so two types. So here we're given examples of oxygen when you partition a container, with a boundary, like a boundary in between. Or you get a lunch box, get the lid, then drop the lid right in the center of the lunch box to just make two compartments. One compartment, if you fill it with oxygen, the other compartment will be filled with nitrogen. When you lift that compartment, what happens is that molecular diffusion will begin to happen. When the partition is removed, the nitrogen molecules will start diffusing into the air, while the oxygen molecules will diffuse into the nitrogen. If we wait long enough, we'll have a homogeneous mixture of nitrogen and oxygen. Liquid in an open bucket of water evaporates into air because of the difference in concentration of the water vapor at the water surface and surrounding area. A drop of blue liquid dye is added to a cup of water. I illustrated this one already. The dye molecules will diffuse slowly by molecular diffusion to all parts of the water. So without you stirring, if you pour liquid dye into a cup of water, without you stirring, you find that after go back to that cup after half an hour or an hour, you find that the liquid would have the dye would have been spread out evenly across that cup, across the liquid in that cup. So we come to Fick's law. We're going to look at Fick's first and second law. Okay, so this is Fick's law. It states that there is linearity between the diffusion of a chemical species and its concentration gradient. So there's a relationship there between the rate of diffusion of a chemical species and the concentration gradient. So what do we mean by that? Well, basically we mean that if this increases, that also will increase. It's a straight line. Then there's also a concept that is known as thermodiffusion. So thermodiffusion is basically a relative motion of the components of a gaseous mixture or a solution, which is established when there is a temperature gradient in a medium. I'll read that again. It's a relative motion of the components of a gaseous mixture or solution, which is established when there is a temperature gradient in a medium. So thermodiffusion happens when you have a difference in temperature, basically. However, thermodiffusion is usually negligible unless the temperature gradient is very large. Then there's also what is known as pressure diffusion, which is a diffusion due to a pressure gradient, which is usually negligible also unless the pressure gradient is very large. So you have movement now of molecules from a place of high pressure to a place of low pressure, same as temperature from a place of high temperature to a place of low temperature. That also happens. Then there's also what is known as forced diffusion. This happens due to an external force field acting on a molecule. So this happens when an electrical field is imposed on an electrolyte. For example, when we're charging a car battery. And also when you look at what do we call that? Ozonation also, we use forced diffusion in water treatment. Okay. So we have an illustration here of water and salt. Okay, so you have salt at the bottom and you have water there. So what happens to the water over time? The water will begin to taste salty also without even you mixing. So what's basically happening is that the molecules from the salt begin to move from this place of high concentration and they begin to slowly, gradually disperse to places of lower concentration. So what you have in the end is salty water after an hour or two, or even after a few days. So coming to molecular transport, slightly different understanding. So molecular transport process of mass is characterized by the general equation. Rate of transfer process is equal to the driving force over the resistance. Is anyone able to tell us the difference between mass transfer and molecular transport?
Come again?
The difference between molecular transport and mass transport. Hmm? Okay. So let's say you take a plate of shima, a plate full of shima from the kitchen, and you take it to the dining room. Is that mass transfer or is molecular transport? There was no shima in the dining room, and the kitchen had the shima. So it's our place of high concentration. So now when you take that plate to the dining room, is that mass transfer or molecular transport?
Mass transfer.
Sure.
Molecular transport.
Sure.
Yes.
Okay. Rate of transfer rate of transfer process is equal to driving force over resistance. That's a formula that we use. So now what is mass transfer? We looked at it, isn't it? We said it's the transfer of molecules from a place of high concentration to a place of lower concentration, isn't it?
Yes.
So is there a chemical reaction happening in mass transfer?
I don't think so.
Hmm?
I think there is.
There has to be, isn't it?
Yes.
The case of rain, absorption. The movement of sulfur dioxide from the air into the water droplets. A reaction had to happen, isn't it? A chemical reaction happens. Then you have SO2 plus H2O, giving you HSO3 to the weak acid, plus what's the other component? That's basically what you get. So you have so meaning there's a chemical reaction that is happening in that particular case. What about molecular transport? Is there a chemical reaction that happens?
In molecular transport, madam, there is no chemical reaction.
So basically, when you carry those molecules of shima from the kitchen to the dining, is there any chemical process that's going to happen that's aiding that transfer, that transport? No, there isn't it? You're just basically moving that mass from one place to the other. No chemical reaction that is taking place. However, with mass transfer, in the case of absorption, so you have absorption, you have a chemical reaction that is actually taking place, that is aiding that transfer. Okay, so Fick's law, we're going to work with Fick's law in our calculations. So it can be expressed as the J. So that's the symbol we use for mass flux action. So this is mass flux. So mass flux basically means mass movement. This is equal to negative DAB. DAB is the diffusivity of a substance. And then there's that fraction there, dPA over dz. So that is change in density over change in direction or distance. So these are these are the units for mass flux, mass transfer by diffusion per unit time and per unit area normal to the direction of mass transfer. So mass transfer has a direction, isn't it? So those movements, that movement of molecules, they're moving in a certain direction, one place to another. So it's direction short and across a certain distance, which we consider in our calculation. DAB, like I mentioned earlier, that is the molecular diffusivity of a molecule A in B. So molecular diffusivity basically just tells us to say to what extent is molecule A able to dissolve into B. So it's calculated in square meters per second. Okay, then that rho A, this is the density of A in kgs per square per cubic meters, and Z is the distance of diffusion. The distance of movement of those molecules, that mass transfer movement, that distance is what we consider in our calculations. Okay. So it can also be across a concentration gradient. So here, if you have concentration values, if you given concentration values, this is how you apply them. So you have diffusivity here happening, and then you have that concentration gradient, which is change. This is the delta CA over delta Z. So this is delta concentration. So concentration 1 minus concentration 2. And Z also Z1 minus Z2. So on a molar basis, the mass flux flow species A in the direction of Z increasing is given by this formula. Okay, so if you're going to say 2 minus 1, then you have to get rid of that negative there. Okay, so let's look at this example here for us to understand how to apply this formula. Can I have someone read the example? Let me just increase it a bit. Too much. Mr. Joshua, please read the example for us.
Given a mixture of the helium and nitrogen gas is contained in a pipe at 298,000 temperature,
That's Kelvin.
Kelvin temperature, and 1 atom total pressure, which are constant throughout. If at one end of the pipe, at 1.1, the particle pressure is that PA1
Yes.
of helium is 0.6 atom is atmospheric, or is atom
Atmosphere.
atmosphere, and at the other end 0.2
Meters.
is that meter
Meters.
meters
Partial pressure A2.
partial pressure A2 is equal to 0.2 atmospheric. Calculate the flask of helium at a steady state if D subscript AB of the helium minus nitrogen mixture is
It's not helium minus nitrogen, but the helium nitrogen mixture.
of the helium nitrogen mixture is 0.687 x,
Times 10.
oh, that's times 10 to the power -4 meter squared per second.
Okay, so the question says calculate the flux of helium at steady state. If diffusivity of the helium nitrogen mixture is 0.687 times 10 to the power -4 square meters per second. Okay, is the question clear? So you have a mixture of helium and nitrogen gases. Okay, these are mixed together and they're contained in a pipe that has constant pressure and constant temperature. So the temperature has been given as 298 Kelvin and the pressure has been given as 1 atmosphere. And these are constant throughout. So one end of a pipe, so remember a pipe has an end, isn't it? It has two ends, basically. So if at one end of the pipe, at point 1, the partial pressure of helium is 0.6 meters, and then the other end, the partial pressure of helium is 0.2 meters. So one end gives us a partial pressure for helium at 0.6, and the other end at 0.2 atmospheres. Calculate the flux of helium at steady state if the coefficient, diffusion coefficient of the helium nitrogen gas mixture is 0.687 times 10 to the power -4 square meters per second. Okay, so now we've been told to calculate the flux. We know the formula for flux already. But then we've been given partial pressures. So in our solution, we say since the total pressure P is constant, okay, so we've been given the total pressure P is constant at 1 atmosphere. C is constant also, where C for the gas, according to the perfect gas law, is PV equal to nRT. So this you should have learned from your previous courses. And then you have this formula here also. Okay. So if this stands true, according to what we've been given, where N is kilograms per mole, which is A plus B, V is the volume in cubic meters, sorry, M cubed. And T is temperature, K, R is this one. This is a constant. Okay, so that's the constant there. Same as this one. So it depends basically on the units that you are interested in. And C is in kgs per mole. That is A plus B divided by cubic meters. So for steady flux, for steady state, the flux in equation 1 is constant. So we've been told that it's this question that we've been asked actually to solve is actually a steady state question. So we know that it means that the flux will be constant. Also, DAB, this is supposed to be small, the letter B here. So the coefficient for diffusion for the gas is constant. Then when you arrange that equation that we're given earlier, this is what we get. Okay. So basically this is what we even had in the first place, except we had delta C and delta Z here. So we should be A minus 2 and 2 minus 1 there. So we lose the negative Y because of the way we've arranged these ones here. So from the perfect gas law, this is what we have. Okay, so when you substitute equation 7 into equation 5, this is what we get. Okay, so what's coming here? We have partial pressure there, and we have our RT coming there at the bottom. So that's the final equation that we're going to use. This becomes our final equation that we use, that we apply in this particular question. So we have our partial pressure there, PA1 minus PA2, we have already. Z2 minus Z1. Which one is going to be Z2 and which one is going to be Z1? So we've been given the distance from the question. We've been given this distance. Okay, so this is the length of the pipe. So meaning one end of the pipe will be 0 meters, isn't it? Then the other end of the pipe, after a certain distance, which we've been given as 0.2 m, that becomes our 0.2 m. So this becomes 0.2 becomes our Z2, while Z1 will be 0 meters. That's why we have 0.2 minus 0 taking place here. Okay. Partial pressure and concentration we calculated using what was given already. Sorry, partial pressure we calculated from here, and we came and brought those values here. We have our R and our T, 298 has to be in Kelvin. Coefficient diffusivity, or the diffusivity or the coefficient of diffusion or diffusion coefficient is the same thing. We place our value there on the numerator and that becomes our answer. So if the pressures in ATM are used with the SI units, then we have an answer in with these this also becomes our final answer, which is the same as this one anyways. So what's worth noting here? In the case where you're given partial pressure, this is going to be the formula that you use. This one here, there's no need for you to derive it. It's in the test. For an exam, you simply just come here. There's no need for you to derive it. So this is what you pick as your working formula, and then you begin to substitute from here. Okay, so this was for molecular diffusion. This is an example under molecular diffusion. So we move to equimolar counter diffusion. So I'll try and send you the recording so that you are able to go through this question. But anyway, we're still going to look at some exam type questions concerning this, maybe to be clearer to you as we go. But I still want us to cover equimolar diffusion before we go to exam type questions. We'll probably look at one or two just to help us get the concept and how it's applied in the exam, in the test. Coming to equimolar counter diffusion is much easier because I think it's more logical. So it tells you that for whatever molecule that leaves, there are two sides, there's A and B. So you have concentration. Let me just go straight away to this. So on this side, we have the blues, isn't it? Which is component A. Component A is highly concentrated on this side. And on this side, we have component B, which is in high concentration. So you have this membrane across here, okay, through which there's this transfer of molecules. So what happens is that for every, so this one is trying to go to low concentration, isn't it? So blue is too much here, it's trying to go to where the white is. The white here is too much, it's trying to get this side. So for every molecule that crosses to this side, the blue molecule, which is the component A molecule, A, B molecule, which is the white one, the white bubble will go the other side. Okay, so for every blue that goes this side, a white will cross to the other side. So it's an exchange, serious exchange here of molecules. That's why it holds counter. So for every molecule transfer, there's a counter molecule that goes the other side to replace it. That's basically the understanding behind it. That's why, hence the term found equimolar. So equi means what? Equal, isn't it? So equimolar counter meaning for one that crosses the one that does the revenge, as we call it. So counter. So equimolar counter diffusion. That's basically the principle under which it works. Okay, so this is just basically explaining what I already said. So the molar flow rate for each species must be equal in magnitude and opposite in direction. That is Na plus Nb is equal to 0. Why is it equal to 0? Because Na is a positive, isn't it? So this direction is positive, going this side. Nb is what? Same magnitude but negative. So if Na moves 5 centimeters, Nb will be negative 5 centimeters. So what do you have at the end? Plus 5 centimeters minus negative 5 centimeters will give you 0. That's the concept here. Na plus Nb. So this one is negative. Nb is actually a negative value. So Na plus negative Nb gives you 0. Okay, so we move on to, let's see else, what else we. Okay, so coming to concentration also, the resulting concentration gradients will cause the species A to diffuse in the positive X direction and the species B in the opposite direction. Assuming the gases to behave as ideal gases, okay, so in the case of ideal gases, you have P is equal to CRT, the total molar concentration of the mixture C will remain constant throughout the mixture. Since P and T are partial, at the partial pressure and temperature respectively. So this is what we get. C is equal to Ca plus Cb, which becomes a constant value. Why? Because based on what we've seen here, so the total molar concentration of the mixture will remain constant throughout the mixture, since P and T are partial pressure and temperature respectively. So this requires for each molecule A that moves to the right, a molecule B moves like I explained earlier. So what moves this side to the right, the molecule also in the same magnitude will move to the left. So hence you have the Na is equal to negative Nb, and hence the 0 there we try to add this two. So this is what we call equimolar counter diffusion, the net molar flow rate of the mixture for such a process, and thus the molar average velocity is 0. Why? Since you have this, okay, magnitude minus this one will give us 0. So that value will basically run as 0. So the velocity basically here is 0.
Madam.
Yes, so yes.
Yes, I think equation 3.5, isn't it supposed to be plus?
3.15 here.
Yes, isn't it supposed to be plus?
Yes, so Na plus negative Nb.
Yes.
Yes.
Okay.
So we mathematically do the same as Na minus negative.
Okay.
Versus 0. Yeah.
All right.
Okay. All right. So velocity. Who remembers the definition for velocity? What is velocity? Anyone remember?
Madam,
Yes.
in simple terms,
Mm.
velocities are the rate of change with respect to rate of change in distance with respect to time, given in meters per second.
The rate of change of distance with respect to time.
With respect,
So when is velocity
yes.
0? Let's borrow from physics. When is velocity 0? When is acceleration?
When
The
is
speed is
velocity equal to
constant.
0?
Velocity is equal to 0, isn't it?
Sorry?
When the speed is not changing, velocity becomes 0.
Yeah. Yes.
So that's what's happening here, isn't it? So hence our velocity here is also 0. because the speed is constant. So we continue. Therefore, the mixture is stationary on a molar basis, and thus mass transfer is by diffusion only. There is no mass transfer by convection. So as a result, this is the formula that we come up with. As a result of that condition. Then coming to, and still under steady state conditions, the molar flow rates of species A and B can be determined directly, developed earlier for one-dimensional steady state diffusion in a stationary medium, noting that P is equal to CRT, and thus this, I think this we've already looked at for each constituent gas and the mixture. So for a one-dimensional flow through a channel of uniform cross-sectional area A, with no homogeneous chemical reactions, they are expressed as, so you have these expressions coming in. So we have to look, I think we probably look at 3 examples, so that we see how we apply which formula. There are a number of formulas and they can be confusing unless you really understand where you're coming from. Okay, so these equations can be written as follows. So for gases, we have this one, okay? For liquids, we have this one. So be careful when you're solving in the test or in the exam. You have to really make sure that you understand the question and which phases are involved, because for gases, we use the specific phase, equation. Whereas for liquids, also there's a unique equation that we use to apply those, where the lambda is the activity coefficient and X is the mole fraction. Okay. So this one, okay, let's ignore this one. I want us to try and look for a question where we'll be able to apply this. Okay, let's try this one in here before we move to an exam paper. So there's this question on venting helium into the atmosphere. So this is the typo, it's supposed to be T. So venting helium into the atmosphere through diffusion. So you need to understand the question very well. Chisala, please read the question for us, the example question here. Okay, can we have Master to read the question?
Come again?
Read the question, please. Example, venting helium into the atmosphere through diffusion.
Okay. The pressure in a pipeline that transports helium gas at a rate of 2 kg per second is maintained at 1 atmosphere by venting helium to the atmosphere through a 5 millimeter internal diameter tube that extends 15 meters into the air, as shown in the figure.
Okay, so this question actually had come, I just remembered. I think about 2 years ago, it came just as it is in the exam. So continuation, so this is what exactly, so okay, we'll look at this later. So just continue reading from here, assuming
Both the helium and the atmospheric air to be at 25 degrees Celsius. Determine A, the mass flow